There are many situations where we're concerned not so much with a random variable itself, but with a transformation of that random variable. And when we're trying to think about the behavior of the transformation of a random variable, we might be interested in understanding what the variability of that transformation is going to look like. In order for us to do that, we need to know how to calculate the variance of a transformation of a discrete random variable. So if we are concerned with the transformation, then how does that transformation impact the variance of the random variable? Okay, so what is the variance of a transformation? Well, to set this up, we're thinking about a random variable x, but we're interested in some transformation of x, which we'll call g of x. Okay? Specifically, what we're trying to understand is the variance of g of x. Now, by definition, the variance of a random variable is always going to be the difference between the random variable, so that's g of x in our case, the mean of the random variable, so the expected value of g of x, all of that squared. Okay, and so if we take the definition, then that's the way that we could calculate out the variance here. Now, in order to actually calculate this, we can find the expected value of g of x using the law of the unconscious statistician, right? We can also calculate the expected value of g of x minus its mean, all squared, using the law of the unconscious statistician. So that's two applications there. Okay. And so, for instance, if we have a discrete random variable, right, then ultimately we can work this out by summing over all of the possible values, g of x minus its expected value squared times by the probability mass function, right? So first we calculate expected value of g of x, then we plug in to this entire expression right here, right? And then that allows us to calculate the expected value of g of x. However, in a more practical sense, we can use the shortcut for the variance calculations. So if we want the variance of a transformation g of x, that is also given to us by the expected value of g of x squared minus the expected value of g of x, and then you square that whole term, right? And so this shortcut tends to be the way we actually go about this in practice, because that shortcut tends to be a lot more straightforward than using the variance definition here. So, taking a look at some examples. Suppose that x represents the number of heads that are seen on 3 tosses of a fair coin. We want to find the variance of x, and we want to find, or the variance of x squared, and we also want the standard deviation of x squared. Okay, and so if we want to find the variance of x squared, well, we need to find the expected value of g of x squared, right, minus the expected value of g of x, where we square that whole term. In order to find either of these, we need the probability mass function for x. And so remember, x is counting up the number of heads that are seen on 3 tosses of a coin. And so we might see 0, 1, 2, or 3 heads, right? If we think about ultimately, well, what is our sample space? Right, our sample space is going to be consisting of 8 total possible options. Okay, and so we can write these out in a few different ways here, right? So we could get a tail, tail, tail. So that's going to be one of the options we could see. We could end up with tail, heads, 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 tails, heads, or heads, heads, tails. Okay, we could end up with 2, I'm going to actually make that our third row here. We could end up with 2 tails and 1 heads. Okay, and so then in that case, we would have something like heads, tails, 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 heads, tails, or tails, tails, heads, right? And then the last possibility is to end up with all heads. And the reason to write it out like this, right, is that this top row corresponds to there being x equaling 0, the second row corresponds to x equaling 1, the third row corresponds to x equals 2, and the final row here corresponds to x equals 3. And so then the probabilities are respectively 1 over 8, 3 over 8, 3 over 8, and 1 over 8. And so good review on how to calculate out our probability mass function here. But once we have our probability mass function, right, if we want the variance of x squared, then here g of x is equal to x squared. And so we want the expected value of g of x squared minus the expected value of g of x squaring that whole term. Right, and so then what is this? Well, the expected value of g of x is x squared, but then we want to square that minus the expected value of g of x, squaring on the outside here. This first term is x to the 4th, okay? And so then what we find is we need to figure out, well, what's the expected value of x squared? What's the expected value of x to the fourth? And then ultimately, whenever we're finding either of those, what we're going to want to do is we're going to want to sum from x equals 0 up to 3, right? And then we're either going to take x squared times the probability mass function of x, or we'll find x to the power of 4 times the probability mass function. Okay, we plug everything in, and then we can work this down. Once we have the variance, if we want the standard deviation, we can take the square root. Okay, so let's walk through all of this in detail here, now that we know sort of the approach we're going to take. Right, so g of x here is x squared. Our probability mass function can be found by thinking about our sample space, right? So we have all of the events that we were writing out there. And so we find a 1/8 probability of 0, a 3/8 probability of 1 or 2, and a 1/8 probability of 3. So then taken together, if we find the expected value of x squared, right, we sum over all of our possible values here, probability mass function times x squared. So that's 0 squared times 1/8, 1 squared 3/8, 2 squared 3/8, 3 squared 1/8, right? And finding that gives us a 3. If we then want to find the expected value of x to the power of 4, right, then we'll need to have all of these be to the power of 4 instead. Okay, so g of x squared is x to the power of 4. And so then we have the exact same formula here, except we're taking to the power of 4 instead of to the power of 2, right? And that gives us 33 over 2. And so then if we want to find the variance now, right, we take the difference. So that's expected value of g of x squared, which was 33 over 2, minus the expected value of g of x, which was 3 squared. And so that gives us 7.5. For the standard deviation, we take the square root, which gives us 2.738. Okay, and so the variance of g of x is 7.5. The standard deviation is 2.738 of g of x squared. G of x, which is x squared. Let's think of another example here. So we have a bag containing 3 red marbles, 2 green marbles, and 4 blue marbles. We're drawing out 2 marbles without replacement, and y is representing the number of green marbles that are drawn. We have the following probability mass function. So what is the variance of y squared? And so again, we're looking at the variance of y squared. So we want to take the expected value of y to the power of 4 minus the expected value of y to the power of 2 squared. Okay? And so to do this, we're going to want to sum over the possible values of y. So in that case, it's 0, 1, or 2. Okay, we take either y squared, so 0 squared, plus 1 squared, plus 2 squared, right? So we square each of these, times by their corresponding probabilities. Or when we want y to the fourth, then we have to make all of those to the power of 4 instead. Okay. And so walking through this, it becomes sort of a mechanical process at this point, right? So the expected value of y squared, 0 squared times 21 over 36, 1 squared times 14 over 36, and 2 squared times 1 over 36 gives us 0.5. If we then want y to the power of 4th, right, we do the same thing, except our exponents are now 4. And so 0 to the 4 times 21 over 36, 1 to the 4 times 14 over 36, 2 to the 4 times 1 out of 36, and all of that gives us 5 out of 6. Okay? So then the variance is going to be the difference between these two. So 5 out of 6 minus 0.5 squared. 5 over 6 minus 0.5 squared gives us 7 out of 12. Okay. What is the standard deviation of 3y minus 2? So here, g of x is going to be 3y minus 2. Right? So we have g, and I guess g of y in this case to keep our variables correct. So that's 3y minus 2. And so then the variance of g of y is going to be the expected value of g of y squared, so that's 3y minus 2 squared, minus the expected value of g of y squared, right? And the expected value of 3y minus 2, we can actually work out using the expected value of a linear transformation. The expected value here, we can use the law of the unconscious statistician to find, and then we take the difference of those, okay? So working through the actual values here, at the expected value of 3y minus 2, we can plug in to our law of the unconscious statistician, so that's 3y minus 2 times, when y is 0, times 21 over 36, when y is 1, times 14 out of 36, when y is 2, times 1 out of 36, that gives us negative 2/3. If we square all of those, right, it's the same formula, except now we have an exponent of 2 on each of the terms. That gives us a 19 out of 6, okay? And so then the standard deviation, we first find the variance, The variance is 49 out of 18, and so then the standard deviation is the square root of that, which gives us about 1.65, say. So the law of the unconscious statistician informs us how to calculate expectations of transformed random variables. However, we can use the similar kind of logic to find the variances of transformed random variables. So we don't need another law, we don't need another theorem. Ultimately, the variances of transformed random variables are expectations that look a lot like the variances of untransformed random variables, and we need the same toolkit to solve for those. So we still need to be using the law of the unconscious statistician, and doing so allows us to work out the variances no matter what our transformation looks like.